Hello dear friends, now we will see the illustration number 6.7 of chapter number 6 and what are the information given in the example. First, as we have studied in the previous session, that potential energy and kinetic energy are the part of mechanical energy, and if the forces is conservative, then the whole energy also conserved. So on the basis of that, we will learn a new example, that is example number 6.7. that is given that a bob of mass small m is suspended by a light string of length L. So here in the figure, that blue color ball is that bob and it is suspended through a length L string. It is imparted a horizontal velocity v0, that is indicated by an arrow. That is, it is imparted horizontally velocity v0 at the lowest point capital A, such that it completes a semicircular trajectory in the vertical plane, with the string becoming slack only on the reaching at the topmost point C. Now all that things are shown in the figure. Here we apply some force in such way that it initially start with the velocity v0. Now it moves in upward path. It will pass through B, and when it reaches to the C point, that is the highest point, it becomes that manner that it experience no tension in it. So it is written that the semicircular trajectory in a vertical plane with the string becoming slack only on reaching the topmost point C. Now as shown in the figure, we are asked three different things. First, that is initial velocity v0, then the speed at point B and C, and third thing that we have to find out, that is the ratio of kinetic energies kb upon kc at B and C respectively. So what we will do here, first of all we will consider that here the force is conservative and therefore total energy also conserved. Now as given in the example, we are having two different information, that is we have to accept. First, the bob experience gravity, that is in downward direction, and it also experience tension towards the center. Now first of all we will find the potential energy and kinetic energy at point A, and on the basis of that we will calculate the mechanical energy at point A. So as shown in the figure, suppose at point A, that we consider as a lowermost point, we consider that the potential energy at point A will be 0, and considering the height as equals to 0, so the potential energy at point A is 0. Now we are given that the bob is imparted with the force that it move with velocity v0. So at point A, the kinetic energy is given by 1/2 m v0 square, and therefore the total mechanical energy, that is equals to EA, where A belongs to point A. So EA is equals to kinetic energy at point A, that is given by Ka, and potential energy at point A, which is given by UA. Now we have already accepted that potential energy at point A is 0, so the total mechanical energy is equals to the kinetic energy, and that is equals to EA is equals to 1/2 m v0 square. So this will be our first equation for point A. Now at that point A, if we go to the figure, we find that as we are given the information that here the tension force is acting towards the center and gravitational force acting in downward direction, but obviously the string is tied to that towards the center, and therefore we can say that here tension force is greater than the gravitational force, and obviously due to this tension force it will perform a circular motion. This circular motion is producing centripetal force, and therefore the equation is given by Ta minus mg is equals to mv0 square over L, where L is a radius as well as the length of the string. So here this will be our another information that is given by an equation A. Now we will move towards the point C, that is the highest point or the topmost point. Here it is clear that as it is given in the information that the tension force becomes 0 at point C and the bob slacks down. So at point C, what will be the information? That is the highest point, and it is given that as a string slackens, our TC, that is tension force at point C becomes 0. Now again we will see the figure. At point C, let us consider that the velocity of bob is vc, and from its initial condition it is exactly diagonally opposite point. It is diametrically opposite point. So we know that as per as diameter is 2 times the radius, and here the radius is the length L itself. So the diameter or the total length will be 2L. Now velocity at point C is vc. So here we can say that the kinetic energy at point C is given by 1/2 m vc square, and potential energy is given by mgh. Here height, that is equals to diameter, and that is equals to 2L, and therefore we can put that potential energy uc is equals to 2mgl. Now total mechanical energy at point C, so it is given by EC, and that is equals to 1/2 mvc square plus 2mgl. Here again the string does not experience any tension, and therefore the downward direction has only one force, and that is gravitational force, and this gravitational force is responsible for that circular motion or the centripetal force. So we can compare, that is mg is equals to mvc square over L, or we can say that mvc square is equals to mgl. Now using this information in equation number 2, so when we put this mvc square value as equals to mgl in equation number 2, we will have another expression for the mechanical energy at point C, that is EC is equals to 1/2 in the bracket mgl plus 2mgl. Now it is very clear that the 2 in the denominator will goes to the multiplication of this term, and as a whole this term becomes 5/2 mgl. So the total mechanical energy at point C is given by 5/2 mgl. Now we know that mechanical energy is conserved. So mechanical energy at point A is equals to mechanical energy at point C. Now we can compare them. As we compare, we can say that EA, that is mechanical energy at point A, is equals to EC, that is mechanical energy at point C. Now we know that at point A we consider it is at the lowermost point, and we consider that there is no potential energy at that point. So at point A the kinetic energy was 1/2 mv0 square, and that is the total mechanical energy at point A. In a similar manner, in equation 3 we have derived that EC is equals to 5/2 mgl. Now replacing these values in equation, we can get V0 square is equals to 5gl after the cancellation of common terms. Now from this, V0 is equals to under root 5gl. So in this case we can get that the V0 is equals to under root 5gl, that is initial velocity that is experienced by the bow. So this was the first question of our information. Now they have also asked us the information regarding the velocity at point B and at point C. So to find out the velocity at point B and at point C, now we will follow the following information. So here from equation B, so again we will move to that equation B. In this equation B, as we see, we can simply explain that is a very well given term, that mg is equals to mv square over L. Now if we cancel out m over here, we have Vc square is equals to gl, and on the basis of that, if we make Vc as a subject, we can say that Vc is equals to under root gl. So this information is given in this equation, and we can say that this will be the velocity at point C. So the same equation that we have applied in the question is obtained over here, that velocity at point C is equals to under root gl, that is obtained from equation number B. Now we are moving to point B. So here information at point B, consider the bob at point B. Now in this condition it will experience again two forces, one that is gravitational force, that is in downward direction, and another that is tension force. Now the total mechanical energy at point B is again given by the kinetic energy at point B plus potential energy at point B. Now we also know that kinetic energy is 1/2 mv square. If we say that the velocity at point B is Vb, then we can say that kinetic energy is equals to 1/2 m Vb square, and the length L is given from the center to the radial part, and therefore the total length and the total potential energy is equals to mgh. Here height is equals to L, and therefore we can say that potential energy at point B is equals to mgl. So that is shown in our equation number 4. So equation 4 belongs to that information regarding total potential energy plus kinetic energy at point B, that is considered as mechanical energy at point B, and it is denoted by EB. Now again we have knowledge that this energy is conserved. So mechanical energy at point A is equals to mechanical energy at point B. Now again we know that mechanical energy at point A is only the kinetic energy at point A, and that is 1/2 mv0 square. Now mechanical energy at point B is given as above equation number 4. So here from equation number 4 we can have the term that is 1/2 mvb square plus mgl. Now we can cancel out the common terms and simplify the term. So if we cancel out the term, and from equation number C above, if we put V0 is equals to root 5 GL, then V0 is equals to 5 GL, and we put this information in above equation, that is given information in this value. If we put this V0 over here, again we can replace it. 1 by 2 5 GL is equals to 1 by 2 VB square plus GL. Now taking the GL in right hand side to the left hand side, we can simplify the term and can write 5 by 2 GL minus GL is equals to 1 by 2 VB square. Now if we simplify the term, we get 3 by 2 GL, that is equals to 1 by 2 VB square. From this we can get another information regarding velocity at point B, and that is VB is equals to root 3 GL. So that will be our information number 2, in which we have calculated two different values. For one at point B we got velocity at point B, and we also got the velocity at point C. So VC is equals to root GL and VB is equals to root 3 GL. That is the answer for point number 2. Now the third point, that is the very simplest part, that we are asked to find out the ratio of kinetic energy. So kinetic energy at B to the kinetic energy at C is given by 1/2 m VB square upon 1/2 m VC square. Now taking cancel 1 by 2 m in both the direction or in both the term, we can say VB square upon VC square. Now the VB is equals to root 3 GL from equation number D, and VC square is equals to GL from the above equation B. Now we can compare and we can say that VB square is equals to 3 GL and VC square is equals to GL. Cancelling GL term in both the ratio term, we can get 3:1. So the ratio of kinetic energy at KB upon KC is given by the term that is 3:1. Now at point C, the string becomes slack and the velocity of the bob is horizontal to the left. If the connecting string is cut at this instant, the bob will execute a projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue to its circular path and complete the revolution. So the motion of projectile that you have already studied in chapter number 4 can be explained with this example, that if the string is cut at point C, it will follow a particular type of path, that from C point, here we can say if this is the circular path, if we say that this is the circular path, in this way object is moving, if it is cut from this or this point, it will go in this manner. So it will perform a projectile motion, but if it is kept as it is, it will complete its whole revolution around the center. So this is the information from this example number 6.7. This is most IMP example, and this is first priority for the teachers as a question for 5 marks. So please prepare this question very properly, and it is most IMP for the exams for 5 marks question. So this was the example 6.7 based on conservative force and the law of conservation of mechanical energy, as it is studied in the previous lecture.